Thank you. Okay, welcome. Good afternoon, everyone. So let's have the last lecture of the day, and that will be about cancer. So again, we're talking about the effect of stochasticity and randomness. And I remind you, I'm doing different systems, different examples where I'm trying to discuss different aspects of stochasticity, right? What we can lecture today in one case was how stochasticity can reduce the noise. And another example was how stochasticity is important to keep, not to reduce. Okay, today is cancer. So when will the cancer start? Let me try to talk with. Okay, so cancer, this is a propaganda slide. All you need to know is serious problem, which you know every year approximately 20 million people got sick and approximately 10 million people died. So this ratio 2-to-1, please remember, right? Because I will ask, you'll see in a moment. Okay, so cancer, actually, this is the cancer death rate in the United States in the last 90 years, approximately. And different colors correspond to different cancers. So this is a death per 100,000 population. And looking at this graph, it's actually quite a good news. The cancer is going down. So the dominating cancer in the United States in lung and bronchus in male. Reason why? What do you think? Why is the reason? Excellent. Smoking, yes. But it's going down. And look, it's starting to going down from 1990 when they started to do this public policy. And right now, approximately 10% of people in America smoke. Very, very low. So when I was student in Russia, almost everyone smoked, especially girls. I probably was the only in my group who didn't smoke. Anyway, so in women, this is also, but it's going down. And there are different types of cancer. Essentially, the more or less reasonably good news for America, but probably for the world too, because America develops drugs which will. Good. So there are many methods of treating cancer, which you probably know, and one of the most successful one, and we already talked with someone, is cancer immunotherapy. This is a very beautiful idea. The idea here is, instead of trying to treat the tumor, let's say, with some harsh chemicals or radiation, what they do is they try to stimulate the immune system of this person to fight it. Because in principle, cancer is that the immune system isn't fully checked. And the idea is beautiful, and there is Nobel Prize was awarded. One of the people I know, he's actually across the street from where I work. He got Nobel Prize. And this works actually amazingly well in old people. And one of the best examples is Jimmy Carter. Do you know who is Jimmy Carter? You know everything. Who is Jimmy Carter? Who was Jimmy Carter? Oh my God. At least from what country? Jimmy, you don't know who is Jimmy Carter? Google. Do not use Google, okay? Jimmy Carter was president of the United States between 1976 and 1980. He is now 100 years old. Approximately 10 years ago, he got cancer, and he was treated with it. And it worked. He's still alive. So it works amazingly well, especially in old people. The problem is it doesn't work so well in young people, relatively young people. So success rate in old people close to 90%, and success in younger people, younger than 40, 30-40%. And the reason is probably the following one. So it's fighting cancer is it's a competition between the immune system trying to develop the ways to kill cancer and cancer cells to spread. And unfortunately, younger people metabolism is fast enough, and the immune system doesn't have time. But in old people, it is. So if God forbid somebody's older grandparent, whatever, get cancer, it's usually not so bad because it's very slow. Okay. So anyway. So, what is cancer? You probably know what is cancer. Cancer is a collection of diseases. There is actually, United States identified more than 500 different types of cancer. It's a collection of diseases of abnormal cell growth. So this cells started to hijack resources from healthy cells. can invade other tissues, and can essentially kill the person. Cancer. So cancer does not immediately come as a tumor, as you frequently want doctors find out. It usually starts with a mutation in a single cell or few cells. This mutated cells start to grow and grow more, and then you have something. Yeah, so people usually divide cancer in several stages. I don't know if this is the same in India. In America, they say stage 0, stage 1, stage, is it the same?
Yeah.
So which actually correlates with the size. So stage 0, 1 is reasonably good, stage 4 is horrible. Yes, but it actually means that the overall development of cancer tumor consists of two big stages. The first stage is cancer initiation, and the second is cancer progression. So cancer initiation, everything is still normal with your organism. There is still okay, but the tumor grows, and then after this there are some changes, physiological changes, and things getting worse. Okay, cancer research. As you understand, there is a huge amount of money spent on doing research. And that includes also India. There are several places in India which do amazing research on science. What I wanted to do something, I want to tell you something today about dynamics of cancer initiation, cancer progression as an important tool for fundamental investigation. And here I make connection with chemistry, but there are other things. So what we do in chemistry, for people who did it, if you remember, we looked at temporal evolution of reactants and products. And when we look at how functional dependence, we can say, what is the mechanism? You remember first order, second order, remember the rest. How we got it? We got it from looking at temporal changes of reactants and products. The same thing is here. The idea is that if you look at the dynamics of cancer initiation and cancer progression, it can tell you what is the microscopic mechanism that led to this dynamic. So this is the idea. And here I want to tell you a story about the very smart doctor. His name was Alfred Knott. That actually was done in Houston. Houston has a Texas Medical Center, which is the largest in the world. Everything is the largest in Texas. So he was 50 years ago. This Dr. Alfred Knott investigated retinoblastoma. Do you know what is retinoblastoma? You don't know what is retinoblastoma? Okay, so this is the main form of very rare but aggressive cancer, which only develops in retina. Retina is a tissue which okay. So and it's only in children. There's the main cancer in children, and it only develops under the age 3. Nobody knows why. And this is typically that's what they see. So I guess you're all young people. When you will give advice to your kids, you will notice. They do the same in India. Doctor will come with a light, flashlight, and he will look at the baby with a flashlight. And the reason for the doctor does this is checking for this, because it's very easy to see. If the eyes have something like this, it's retinoblastoma. There are, as people say in America, the good news and bad news. The bad news is cancer, and you might eventually lose sight. The good news, it's 98% of the survival rate. Okay, and it's doesn't give metastasis. So in the worst case scenario, you just remove something. The person loses the sight, but the person does not die. It's quite rare. So I think in America, it's a order of 500 cases per year. This information that they found in India, approximately 8,000 children born with retinoblastoma. Please remember when you were giving the birth, remember me, right? The flashlight is checking the baby for retinoblastoma. Anyway, sorry for distractions. So this Dr. Knudsen was a very smart doctor. He actually decided to do the following thing. He was treating this retinoblastoma. He had like 48 cases, and he asked patients only one question. He asked patients, parents, kids couldn't say, are your parents or grandparents also had this disease? Essentially, he was asking, is this hereditary or not? You understand, right? So then he divided all patients into groups, hereditary and non-hereditary, and he plotted this data in this graph. So this is the time, age in months. This is a fraction of cases not diagnosed. You start always from 1, and 0 is 1. He realized that those patients who were hereditary, whose parents and grandparents had this, were according linear curve in this coordinate. Those who were non-hereditary had kind of parabolic, quadratic thing. The doctor was smart, and he realized, you have to understand, it was 50 years ago. The knowledge about genetics was much smaller. He realized that this is what's happening. As you know, we have two pairs of chromosomes with identical set of genes. He realized that those people who hereditary, already one of this gene was mutated, and you had to do only one more mutation, completely knock out gene from both, and that's it's a single step. But those who were non-hereditary, you had to do two steps, called two hits. So that's why there is quadratic in time here, linear here. Make sense? Do you understand? Very smart doctor. And that he came out with the idea that there's a tumor suppressor of genes. Do you want me to repeat, or is it clear what he did? Repeat, okay. So he asked 48 patients, are they hereditary, non-hereditary? If those who were hereditary, whose parents or grandparents had it, he plotted them, data, this is a square, and they were on linear graph in this coordinate. Please note that this is logarithmic. Those who were non-hereditary were quadratic in time. And then he realized, for normal people, you need to do two events before you get cancer, quadratic in time. But for those people who need only, for hereditary, one gene was already damaged, you need to do only one step. This is a classical case. This is a classical case when smart person looking at dynamics can tell you something about microscopic phenomena. Okay? That's exactly what I want to do. I already emphasized this in serious lecture. So this is yes, and the gene for this retinoblastoma was discovered in 1986. So those are genes which, if you mutated them, cancer can develop because there is no way of suppressing them. And the most famous one I already mentioned, P53, right? P53 is a gene. It's a protein which responds to stress level in cells that's responsible for 70% of the cancers. And there's some also breast cancers. For breast cancer, there are additional things here. Okay. So this is what we want to do. We would like to try to understand the microscopic mechanism of tumor development by analyzing dynamics through stochastic modeling. And we look at the simplest possible situation. We only look at cancer initiation. This is the early part when you start from a single cell mutated and so on and so on. Okay, so it's important to talk for a moment where cancer comes from. It's a random mutations in oncogenes, random mutations in genes. If you knock out those genes, it will lead to cancer, and it happens by place, random, by chance, pardon. It doesn't matter if you would live somewhere, I don't know, Hawaii, in perfect climate, you still have a chance to get it, unfortunately. It's a bad luck disease. Cancer is a bad luck disease, and it unfortunately happens by chance. How mutations are happening? Mutations are happening in the following way. Remember, we talked about it, that cells have to replicate. Most of the cells are called stem cells that have to replicate. Replication of cell means that you have DNA, you have to create exactly the same DNA, right? But it's happened in this environment where many similar molecules, so mistakes are possible. Right? We talked about, if you remember, biological error correction. Yes. So nature knows this, and nature has a lot of this DNA repair pathway. And it works amazingly well. It works with a precision 99.99969%, but not 100%. It's not 100%, and there is no way, there is no time for cells to fully correct everything, right? So cancer is a bad luck disease, and I will repeat it many times. So many things should go wrong to get cancer, unfortunately. Okay, so if we all live 1,000 years, we would all die from cancer because of the more the stem cell divisions lead to higher probability of cancer. Now, I'm not trying to tell you don't drink, don't smoke, okay? Because these bad habits increase the probability of this. But even if you're a perfect world, you know, there is a chance for this to do, unfortunately. Okay, good. This is a kind of a proof what I told you. So apologies for the quote, unfortunately that was the best I can do. So these people did several measurements and collected data in the United States as well as in the world. So what is plotted here is each point corresponds to different tissue, different number of stem cell division. Different tissues has different number of stem cell division. stem cells are those cells that divide. So the division of the stem cells can lead to error. And this is lifetime risk. Lifetime risk. So as you can see, the more probable things to divide, the higher probability of cancer. It's like your cell phone. If you charge and charge, there will be, the more you do it, the sooner it will die. Something like that. Okay, good. So we introduce the concept of cancer lifetime risk. What is it? It's a probability of being diagnosed with or to die from cancer. So it's a probability to die or being diagnosed with cancer. And let me show you the data for United Kingdom for 20 most common cancers. And the blue color is for males, the magenta for female, and this two is for all, and then for different types of cancer. So you can see the British man, the dominating is prostate. I think food is horrible, that's the reason. Dominating. Women is breast cancer. But the most scary thing is that the probability for United Kingdom male to get a cancer is 50% in lifetime. It's horrible number, very scary number, right? And we'll go to other countries. United Kingdom is one of the worst cases, so don't worry about it. Israel is much better. So for every country there is a data like this. I try to collect it as much as possible. It gives you this population at the moment of measurement, this how many cases. So you see the ratio 1/3, right? That's a good sign. It's a sign of a good medicine and good taking care. Remember I told you about 2-to-1 ratio, right? You will see it in a moment. Here comes Italy. Here comes Italy. Not as good as Israel, still reasonably good. This population of Italy, this number of cases, this number of deaths ratio, less than 1/2, right? Reasonably good. Israel and Italy probably have this Mediterranean diet. The food they eat is reasonably good. Sun is enough. The dominating cancer is also in male is the prostate, in female is the breast one. Typical one. Let's go to India. I didn't find the same information, but in India, approximately close to 1.5 million cases, the number of deaths close to 1 million. It's not good, as you can see. Ratio is not 1/2. Something is not okay with medicine or whatever. But this is the number of people who survived over the 5 years. So the dominating, the main cancer in females is still breast cancer. But the one in males is lip oral. Can you tell me why?
What? Which one?
Huh?
Betel.
Betel. Okay, so India has the highest rate of lip oral cancer. Easily can be avoided, easily. Okay, so anyway. So we're talking, okay, let's go back to cancer lifetime risk. When we talk about probabilities, and it's not only cancer, it's about any events in our life, right? We usually, if something is more probable, we subconsciously think that it will happen sooner, right? And because we think that probability distributed uniformly, but that's might not necessarily be the case. Nobody checked it in cancer. In other words, they scare you, oh, this probability with cancer is 50%, you have to do something, right? The most stupid case was Angelina Jolie, who removed, she did this operation because probability was high. Anyway, not the smartest woman. So good. So let's come back to cancer. So we'd like to model the cancer, and we again encounter this phenomenon of homeostasis, right? Already repeated homeostasis maybe 20 times. So one of there is a tendency to maintain constant physiological parameters, and actually the number of cells in grown-up organisms is almost constant. So the number of stem cells in grown-up organisms is almost constant. But I'm simultaneously telling you that they divide, how it can happen, right? So apparently there are some mechanisms which remove. So they divide, remove, divide, remove. We don't know exactly what are these things here, but for modeling purposes, most people who do mathematical biology argue that you can apply something which is known as a Moran process. Well, let me try to, okay, some people already know, so you heard about it, but let me try to explain you from the point of view, if you do Monte Carlo simulation, this is how it works. Imagine there's a tissue with 10 cells. You randomly choose one of those cells and you divide it. and instantaneous you have 11 cells in your first substep. In the second substep, you randomly choose one of those 11 and remove it. As a result, you will have 10 cells, but the state of this tissue, this might not be the same. That's the idea. But I want to emphasize this is a mathematical procedure. We don't know exactly how nature does it. Good. There comes stochastic model. I actually explained to you everything what you need to develop stochastic model. So let's consider a normal tissue, and we typically know number of cells. The number of stem cells, those cells that divide, are ranging between 10 to the 5 to 10 to the 20. We know for every tissue number of cells. We know. So this number is known. Let's assume at some time zero, let's call time zero, mutation happens. This very, very unlucky event is a probability 10 to the minus 8. Mutation happens. So in our analysis, let's consider only so-called driver mutations. Driver mutations are those mutations in these genes lead to cancer, because there are many other mutations called passenger mutations. This is the slang that people use in this field. So important mutations, we only consider important mutations. Mutated cells are characterized by one number called fitness parameter. What is this number? This is a number which tells you how faster the division rate of mutated cells in comparison to the division rate of the normal cells. By the way, division rate of normal cells are known. I think I mentioned typically 1 per day. So this is a number, and this number could be larger than 1, equal to 1, or less than 1. So if it's larger than 1, mutations are advantageous. If it's less than 1, it's called disadvantageous, and if when it's equal to 1, it's called neutral mutations. Again, we need to maintain homeostasis. So we are modeling cancer initiation. Everything is still normal with the organism. So you have to follow homeostasis. Not normal, no homeostasis. That's the reason. Normal, you have to follow homeostasis, so the number of cells should be fixed. So
this is a hypothesis.
No, that's known. It's known that the first stages of cancer, everything is still normal. Okay? For me, this is the beginning of cancer when things become not normal anymore and you cannot use homeostasis. Then it will be progression. Okay? I'm trying to model this first stage. So again, I do this Moran process as I explained to you. I don't assume any mutation. So essentially, the state of my system is I can always describe the state of the tissue with a number. So this number tells me how many mutated cells. In this case, 2, 3, and so on. So I started with 1, and there are transitions to, I can completely remove mutations, or I can go stochastically change between states. And for me, it's the beginning of cancer when everything becomes, all cells become mutated.
And what is R considered here? Is it greater than 1 or what?
You will see it in a moment. I can ask you what is this formula in a moment. Okay. But the important thing for me, this is a mutation appears, but organism still okay. Okay? And then stochastic transitions can happen, following the rules that I explained to you. But eventually, you randomly can come into this state. And I call this fixation, or this is the appearance of tumor in my language. Okay? So, and that's what I want to do. I want to calculate dynamics to reach to this state. Is it clear? Again, stochastic approach. So I can calculate this rate. I already given you the answer on this rate. So these rates are non-linear. It depends on the current state, the current number of mutated cells, total number of cells. It's non-linear.
What is B here?
B is the division rate of normal stem cell. It's typically 1 per day. So it's known. So it's known. Okay. So that's it. I have a model. I have an extremely simple, probably very stupid and very naive model of cancer initiation, which is viewed as a change of stochastic transitions with the rate that I can determine from this Moran procedure. And I can do the calculation. For example, I can calculate what is the probability that I will do so-called fixation. In this business called fixation, what the probability to start here, I can reach this one. It's not 1. That's because there is possibility of actually everything. So cancer is a bad luck disease. There are so many things has to go wrong to get it. So this is one of those. I can also calculate time. This is mean first patch time. By the way, you understand this is the first passage calculation, right? This is a splitting. This one is a splitting probability to reach this state. This is mean first passage time, conditional to reach this point. Okay, so I have a theory, I can do the calculation. So I have, of course, the important things to apply to medical data. There's a huge amount of data. Data is for America, where it's reliable. So to apply to medical data, I only need to find out this one parameter. The rest is known. Only I need to find out the fitness parameter. I need to find out how to do it. So let me give you arguments that which goes back to Mark Noor, who is quite famous mathematical biologist, but arguments are easy to explain. So this is the argument. Let's assume a person lives 80 years. Okay? If a person lives 80 years, I can calculate the probability of cancer initiation. How to do it? So the B is division rate of one normal cell. NB will be total number of cell divisions, right? Then if you multiply this in B by T life, it will be number of cell divisions during the lifetime, right? So NB is the rate of total number of divisions per unit time. If you multiply it by human lifetime, it will be total number of cell divisions during the lifetime. Okay? And then you have to multiply by probability of the first mutation, which is very low, but not zero. And then you have to multiply by the probability of fixation. This fixation that we have it, okay? This formula already is not the end yet, okay? And this is only probability of initiation. Then you have to multiply by probability of cancer. Remember, initiation and progression. How do I get this number of probability of cancer progression? Mammography. Do you know what is mammography? Do you know what is mammography, right? In America, you know, nothing is free in America. It's only free things in America. Women up to 40 get this for free. This is an important thing. So any woman older than 40 should do mammography once per year. Okay, and it's not only good for health. By the way, breast cancer is almost curable essentially. So that if you don't go to stage 3 or 4, they give you pill, and there's almost no side effects. 5 years, and that's it. So that's why Anatoly was very good. Anyway, so mammography collected huge amount of information. The way it works, they have some how to explain. It's not X-ray, but similar things which and they look, and if there is an increase in density somewhere, then they ask again and do. So they collect huge amount of information. And the point here is that only 0.1% of those cases that they think might be cancer turned out to be cancer. Again, cancer is a bad luck disease. So many things should go. I told you already 5 or 6 checkpoints, right? Wrong. Good. So encourage your parents or grandparents. They have to do it. I'm pretty sure they have something like this in India. It's important things every year. Okay. Mammography. Good. So I have my theory. I can calculate what I needed. So essentially, you understand. So using this approach, I can estimate the fitness parameter. That's all I needed for my theory, and I can calculate it. So, okay, so I calculated for 30 different types of cancer. What will be the time before cancer will start in different tissues? This is time in years. I only show 6, the most typical one. Some of them are not bad, 15 years, but some of them are ridiculous. Why they are ridiculous? Tell me why these numbers are ridiculous. Not why they think it's ridiculous. What's wrong? What I implicitly assume in my theory, that you live forever, that your metabolism is the same rate forever. We don't live forever, right? So you should probably do not. My apologies for the quality. It looks better in my computer. I don't know. The only one. You cannot trust these numbers, probably, right? It's a very crude theory, but you can probably trust the trend. Probably the trend will be okay, right? The one is a more probable cancer, or the one which will come sooner. So you can still apply this theory as long as you do not oversell it, as long as it's qualitative, semi-quantitative. Okay, good. And you can answer the question. Remember, I posted the question: if something is more probable from the point of cancer, will it happen sooner or not? That's right. So we checked it. It's not. And so what I plotted here: lifetime risk for 30 different types of cancer, and this is measured. I get it from data from the National Cancer Institute. Here, fixation time that I calculated with my theory. if there is a correlation, I would expect the points to be on this diagonal, right? Something more probable should happen faster, less probable. It's not. There is some, but it's not. You expect -1. And you can do statistical analysis, no correlation. So if you can believe my theory, there's no correlation between, in principle, between probability of cancer and time before it will come. So this is a very important prediction because so the doctor should not scare you with the probability. They should give information. What is the average time before this comes? And by the way, the existence of this children cancer is another example that it's not necessary correlate probability and time before it goes. Okay, so both properties must be used in evaluating the cancer. Good. This is surprising, right? For you that something is more probable doesn't happen fast, but it's actually not. Chemistry is one of many examples when it's happening. So, for example, chemical reaction. Suppose this is a chemical reaction. What is the probability of chemical reaction? Probability of chemical reaction given by the free energy difference between product and reactant. The lower energy the product, the more probable the reaction. But the fact if reaction really happens is not this delta G. It's this barrier, right? If the barrier is huge, reaction will not happen. So the paper should not exist that you have some paper because CO2 and H2O are thermodynamically more stable. Who has diamonds? Girls. You have diamonds? Okay, husband will give you presents. You have to be happy because diamonds thermodynamically unstable. Do you know what is this? Coconut, right? The most famous one. Graphite is more thermodynamically stable, but it is almost impossible to change diamonds to graphite. I don't know what's the people who do it, but it's almost impossible because the barrier is huge. So if something is more probable, doesn't mean that it happens. And remember about diamonds or paper. We should not exist because carbon dioxide, H2O, nitrogen, and oxygen are thermodynamically more stable than we are. That's why we eat. If we wouldn't eat, we would die and we'll go to CO2 or nitrogen, whatever. So, yes. So for a moment, let's come back to cancer and let me argue why this is important. Okay. Why what I'm telling you is important that it's not necessary, even if it's more probable, it's not necessary to happen, and this is the case that there's no correlation. That's because it means that when I go from here to here, there is probably some kind of a barrier. If this is a barrier, okay, so the dynamics reflect possibility of barrier. If this is a barrier, then that could be a target for medical therapies. If you can increase this barrier, make it stronger, then your probability of cancer will go down. Okay, again, this is an example. You look at the dynamic, okay, very simple model, but it can give you some more important microscopic information. Extremely simple stochastic model can give you some information. Okay. Okay. Good. There is another interesting story related to this one, and I want to tell you these things because it will show you the power of stochastic model. So I told you a nice story about the doctor from Texas, Nancy, right? And he argued that you need to have two hits, two mutations to get it, right? But the theory I told you was only one mutation, right? So it turns out, maybe you know this, that actually in many cases you need between 2 and 8 mutations, so-called hits in this business before cancer will come. Again, cancer is a bad luck disease. To have the probability of 8 mutations, you really have to do something. Something should be bad. Anyway, the smallest number of mutations in the brain, in glioblastoma. And that's one of the reasons the brain cancer is probably one of the most serious ones because it's only 2 hits, it happens fast, and the drugs typically do not work because of so-called blood-brain barrier. Okay, so different tissues has different number of these hits before cancer will come, and then comes interesting observation. So, as you probably know, most of the measurements, most of the studies on cancer do this in mouse, right? There's plenty of mouse, and they studied this adrenocortical tumor. This is over there. Anyway, so they noticed the following thing. This cancer should have 2 mutations, one called RAS, another one P53. But they were able to notice interesting things. So that if you have first mutation RAS, first in time, and then come P53, you get some horrible cancer, malignant metastasis quickly. But if you get first P53 and then RAS, you get benign tumor. Benign tumor is nothing wrong, you remove it and that's it. The same cancer, the same eventual outcome, two different things. Okay, so this is interesting. So then comes another observation. So this is another horrible cancer called blood cancer. The only good thing about blood cancer is that you can collect a lot of information, but because patients have to give blood samples very, very frequently. So again, two mutations are needed, TET2 and JAK2. So they notice that in all cases there are blood cancer patients, but those who had first TET2 and then JAK2 lived approximately 10 years longer. Those which had JAK2, TET2 had less, lived shorter. The same cancer, the same final set of mutations. How it's possible? Stochastic picture that I told you can explain this thing. So it's essentially, this is the story. So there is a different outcome if you go AB versus BA, right?
So
And
the mutation takes in one order. Is it always going to take in that order only, or it can?
random, as far as I understand, random.
Okay.
But the point here, people couldn't understand why. You have eventually got 1 million rupees. Somebody gave you 500, another one gave you 500, right? But in one case it was drug dealer, another case was your parents. It's the same amount of money at the end, right? But it's not the same story, right? Something like this. I don't know how to explain it. But there is no explanation. But the theory can explain. The stochastic theory can explain, because the stochastic theory has this implicit assumption that cancer initiation is effectively stochastic process, that you are moving in effective free energy landscape. And going AB, there is one path, going BA, it's another path. If you understand that, right? So we can modify the theory. We can say there's a possibility 0 mutations, 1 mutation, 2 mutations, and again it's a sequential process, and you can calculate it again things analytically, and AB is not the same as BA, and you can get something like this. So if first mutation is more advantageous, it means more advantageous means the barrier here is smaller. The first one is smaller than the second one. What you're getting is the overall probability of cancer is higher, but time is longer, because you start here as a barrier. Okay? So this is good for beneficiary probably for people. This is better. If situation is opposite, the first mutation is more, and it is less advantageous, the barrier is higher. The overall probability is lower, but you go faster to your cancer. Okay, so it's not the same thing. So this is the stochastic model, stochastic picture effectively assumes there are different pathways, and if it's different pathway, will be different time. We have seen something like this in this course, different pathway, different times. What was it? What was it? Something we talked about some phenomenon, different pathway, different times. What we discussed some phenomena when there is going one way, there is one rate, you go another way, there is another rate. But the initial and final path of the same, initial things and final things are the same. The path is different. Do you remember? Start with C. Second letter A. Catalysis. Catalysis is an example of this. I mean, it's not Z, but related phenomena. Catalysis, there is no change in initial and final state. The only catalysis that provides a different path. It is different pathway, different time. It's exactly what is here. Okay? So I wanted to make connection with chemistry with this, and all this comes from relatively simple stochastic description.
Sir, is there any theory which talks about like minimum number of mutations for the initiation of cancer?
No, I don't know. This is a difficult question. I don't know. It's not trivial question, and so essentially. As I mentioned, cancer is a bad luck disease. So for some tissues, 2 mutations is enough to disrupt. But for others, you need 8 mutations to disrupt everything. I don't know. You need to know much more biochemistry, and I don't know to do it. Good. So this is essentially this theoretical predictions. You can essentially, if the theory is right, which might be wrong, you have to understand, right? It's a very naive, crude theory. The probability of overall cancer initiation is determined by the first mutation, but the cancer mutation time depends on both mutations. And if the acquisition of more advantageous mutation at the beginning increase the probability of tumor formation, but related cancer initiation. So, but the theory can explain this, okay? Maybe the theory is wrong, but there's nothing else in the field can explain this thing by using this analogy. So this is it. We actually came almost to the end. So I wanted to show you that even such a complex phenomenon as cancer, you can use some stochastic analysis, and it works reasonably well. It's oversimplified, right? It's oversimplified. The cancer is much more complicated than it's. The theory with one fitting parameter definitely cannot feed this thing, right? But still, it tells you something. It tells you something that you can calculate eventually many things here. We applied it for this clinical data for cancer. And the most important things I'm trying to emphasize here, lifetime risk and cancer initiation in general do not correlate. That's an important news. Okay? And stochastic framework is successful to explain not only cancer initiation, but as well as this order of mutations. Order of mutations. It's another example that science works by analogy. You find something in one field, then you can apply it to another one, and that helps you. Okay? This is it. This is cancer. This is the end of the story. If you have any questions, please. I hope I didn't scare you.
No.
So, if we would live 1,000 years, we will all die from cancer. Okay, the older population becomes, the more probability of cancer increases. But we understand. People understand more, and there are better drugs. For example, breast cancer is essentially almost curable. Prostate cancer is almost curable. One of the most dangerous things is brain cancer. By the way, the recent data shows that up to 50% of our skin cells are already mutated. So use sun protection. Who uses sun protection? Girls, okay. But boys, you should also use sun protection. Skin cancer is melanoma, it's dangerous. You have to use also, okay, girls use it, but you have to use protection over the. Yeah, there are a few simple things can help. Food, don't smoke, drink less. They cannot drink, but less. Don't drink too much, okay? Don't drink too much. By the way, some people argue that red wine a little bit, 1 glass per day is okay. Okay, by the way, when I was in the Radun, the lady professor told me that apparently in India they sell a test. If you do this test, you can tell if this person can get cancer or not. This is absolute nonsense, right? There is no way that one test can tell you. Okay, so do not follow. Your educated people do not follow. Cancer is a very complicated thing. It's a very heterogeneous collection of diseases. There is no such thing that can tell you from one test. There is a story in America that maybe you heard about. It was a company called Terra Nova. It was a lady, which actually she was from Houston. Then she got the first. She was in 1 year at Stanford. She was very smart, undergraduate in Stanford in bioengineering, and then she decided to open a company and said from one small drop of blood, she can immediately determine 400 diseases, right? Her company collected $4 billion. So people are really stupid and uneducated, okay, investors. She eventually ended up in jail. But if you look at this, it's called Terra Nova. But it was for scientists, it was obvious. There is no way. So don't fall into false claims. People are easy to make money. One of the easiest ways to make money is to scare people. Don't be scared. Nothing is the end of the world, even the worst cancer. There is always a way to do it. The story of Jimmy Carter, who you should know who is Jimmy Carter, okay? Good, at least someone knew, okay, but he came later. Oh, you checked it, okay, Google, thanks to Google. He was not the most successful president, to say politely. But that's a story. There are many other stories. Okay, we finished.
Yeah.
Okay, any questions? I know I made it a little bit more entertaining than there are mathematics here, believe me. I just removed it. But because there is a story here that you can use. Okay. Any questions? If you want, we can talk over.
Sure. Let's thank the speaker for a wonderful talk.